Right now, out in the high desert, there is this massive server farm humming away in the dark.
Yeah, just quietly chewing through data.
Exactly, like billions of photographs and text logs and sensor readings. And the wild part is, there isn't a single human being sitting there telling it what a tree is or what the sky is.
Right, or what an angry tone of voice sounds like.
Yeah, it's just figuring out the shape of reality all by itself.
Yeah,
It's taking this raw, completely unlabeled chaos, and it's somehow finding a hidden structure.
which is, I mean, it's a complete departure from how we normally think about problem solving, right?
Totally.
Because we're so conditioned to expect this clean binary system. Like you go to the doctor with a broken arm, they take an x-ray, you get an objective truth.
The bone is broken, or it's not broken.
Exactly. You have an answer key that's provided by an expert.
But the modern digital world has basically broken that X-ray machine.
Oh, completely smashed it.
Yeah, because the sheer volume of data we generate every single second, I mean, trillions of digital footprints, we're just drowning in it. There is no doctor to point at the screen anymore.
Right. There's no truth handed to us on a silver platter. We have all this data, but we don't have the labels.
And that specific scenario where you're forced to learn about the world without any labels at all, that is the absolute definition of unsupervised machine learning.
It really is. And it's not just some niche computer science hurdle. It's actually this profound epistemological question.
Like, how do we know what we know?
Exactly. It asks how any intelligence, whether it's a human toddler or an artificial neural network, can build a reliable model of reality when literally no one is standing over its shoulder giving it the answers.
So if you are listening to this on your commute right now, or maybe while you're making dinner, welcome to a very special deep dive.
We have a huge journey ahead of us today.
We really do. Our mission today is to journey into that totally untamed wilderness of unsupervised learning. We are going to start at the very bottom, taking a huge, messy pile of data and just figuring out how to group it.
The foundational stuff.
Right. Then we'll learn how to whittle down the noise, how to literally morph the remaining pieces into entirely new concepts.
That part is always mind-blowing.
It's so cool. And then finally, we're going to drill all the way down to the 1940s to uncover the fundamental mathematical core of what the word information actually means.
It's quite the itinerary. We're moving from just practical grouping all the way down to the literal physics of knowledge.
It is ambitious, but before we pack our bags, let's just set some ground rules for you, the listener.
Oh, yes. Very important.
This deep dive is a strictly math-free zone.
Highly strictly.
Yeah, we are not going to be reading off Greek letters, and we definitely don't expect you to solve differential equations in your head while you drive.
Please don't do that. Keep your eyes on the road.
Right. So instead, we're going to rely entirely on intuition, some really vivid, real-world analogies, and a few thought experiments to map this out.
Which, honestly, is truly the best way to understand the architecture of these systems anyway.
I completely agree. So where do we start?
Well, before we can measure data or filter it, we really have to perform the most basic cognitive task. We have to organize it. We have to group things.
But grouping things inherently requires knowing what the groups are, doesn't it? Like, if I ask you to organize a messy room, you naturally make a pile for clothes, a pile for books, a pile for trash.
Right, because you already possess the conceptual labels for clothes and books.
Exactly. But if you wipe those labels completely from your brain, how do you even begin to clean the room?
You begin by shifting your focus away from the labels entirely. You look at the relationships between the objects themselves.
Okay, so ignoring what the thing is and looking at how it relates to the other things.
Precisely. In supervised learning, you have a cheat sheet. You feed a computer 1,000 pictures, and every picture has a giant human-applied tag that says CKT.
So the algorithm just learns how to map the pixels to that specific tag.
Exactly. But in unsupervised learning, the classic foundational problem is called clustering. You just have the massive pile of pictures. And to create structure out of that, you only need two ingredients.
Okay, what are they?
You need the set of objects themselves, and you need a definition of inter-object distance.
Okay, wait. Distance in this context doesn't mean pulling out a literal tape measure.
No,
Yeah.
not at all. Distance is just a mathematical proxy for similarity.
Let me try to visualize that.
Huh.
Let's say we are clustering a massive database of movies. The distance between two movies might be calculated by, I don't know, how many of the same actors they share.
That's a perfect example. Or maybe the overlap in their genre tags.
Right. So a lighthearted romantic comedy and a super gory slasher film have a massive distance between them in this space.
Even if they were technically filmed on the exact same physical soundstage in Hollywood. The geographic distance is 0, but the feature distance is huge.
Okay, I track that. The domain knowledge you use to define that similarity feels like the secret sauce.
It absolutely is the secret sauce.
Uh,
Because once you define what makes two objects close together or far apart, the goal of clustering is simply to produce a partition,
a partition, meaning like drawing a line in the sand.
basically. It's a rule that dictates which objects belong in group 1 and which belong in group 2.
But without an answer key, evaluating whether you actually did a good job seems entirely subjective.
Oh, it is highly subjective.
But like, for instance, I could look at a database of every single animal on Earth, and I could just put every single one of them into one giant cluster called Earthlings.
Mathematically, you haven't broken any rules there. Every object is technically assigned to a cluster.
Right. It feels useless, but it's valid.
It is mathematically valid. It's known as a trivial partition. All objects in one universally encompassing cluster.
Okay, so what's the opposite of that?
The inverse is equally trivial. You could look at that same database of animals and assign every single animal to its own unique individual cluster.
So an endless sea of clusters containing exactly one item each.
Exactly. We are all beautiful, unique snowflakes.
Well, if the we're all one approach and the unique snowflake approach are both technically valid, that implies something kind of huge.
What's that?
It implies that the true cluster doesn't actually exist out in the universe waiting to be found. The clusters only exist based on the specific algorithm we choose to run.
That is a brilliant way to put it. Clustering is highly algorithm-driven. You are literally applying a specific mechanical philosophy to your data.
Okay, so let's look at some of these philosophies. What's the most basic one?
The most intuitive place to start is a philosophy based entirely on local neighborhoods. It's an algorithm called single linkage clustering, or SLC.
Single linkage clustering. Let's call this the closest friends approach. Let's try to paint a picture for you listening. Imagine a massive white whiteboard.
Okay, a huge blank whiteboard.
And I've taken a black marker and drawn 100 random dots scattered all over it. How does SLC start grouping those dots?
It actually begins with that snowflake philosophy we just talked about. It assumes every single dot on that whiteboard is its own independent cluster to start.
So we start with 100 clusters.
Right. Then the algorithm scans the entire board. It measures the distance between every possible pair of dots, and it asks a very simple question.
Which is?
Which two dots are the absolute closest to each other out of all of them?
Okay, so it finds that one specific pair that are practically touching.
Exactly. It finds them, draws a circle around them, and merges them. So now you have 98 single dots and one cluster of 2.
Got it. Then what? It just loops.
It just repeats that exact process. It scans the board again, looks for the next closest pair, which might be 2 individual dots, or it could be a new dot that's incredibly close to our newly formed 2-dot cluster.
Oh, I see. So it just merges whatever's closest, building up from the ground.
Yeah, it builds a tree from the ground up, constantly merging the closest available entities.
But wait, how does it define the distance between two clusters once they actually have multiple dots inside them? Like, where do you measure from?
That is the critical mechanical question. Single linkage clustering has a very specific literal rule for this. The distance between any two clusters is defined exclusively by the 2 single points within them that are closest to each other.
So it completely ignores the centers of the clusters.
Completely ignores them.
So if I have a really dense cluster of 20 dots on the far left of the whiteboard and another dense cluster of 20 dots on the far right, it only cares about the one specific dot on the left side reaching out and the one specific dot on the right side reaching out.
Yes, the ones that happen to be geographically nearest to each other. It only looks at the absolute shortest possible bridge between the two groups. It ignores the vast majority of the points.
Okay, I can see a massive visual flaw with that logic.
Oh, it's a very famous flaw. Walk me through what you're picturing.
Let's say we have 2 very distinct, tight circles of dots on our whiteboard. To the human eye, they're undeniably 2 separate groups.
Right.
But just by pure random chance, there are 3 or 4 stray dots scattered loosely between them, like a very sparse, weak little path of breadcrumbs connecting the 2 dense circles.
Single linkage clustering will walk right across that path.
It will!
Yes.
Yeah.
Because those stray dots are relatively close to each other, the algorithm will merge them into a chain. And because that chain eventually touches the edge of the first dense circle and the edge of the second dense circle, the algorithm will proudly declare that the entire massive structure is just one single giant cluster.
Even though the 2 main circles are super far apart.
Exactly. It creates these weird, long, barbell-shaped blobs.
That is essentially the friend of a friend problem at a dinner party.
Ah, how so?
Like, you get invited to a dinner because you know a guy who happens to know a guy who goes to the same gym as the host.
Right, right.
Suddenly, you're sitting at a table with 30 people, wondering how you all got grouped together, because the person at the far end of the table has absolutely nothing in common with you. You were just dragged into the cluster by a long chain of weak individual links.
That is a perfect structural analogy. Single linkage clustering is incredibly simple, and it's deterministic, meaning if you run it on the same whiteboard 10 times, it draws the exact same clusters 10 times.
But those long, stringy chains are a problem.
A severe liability if your goal is to find tight, cohesive groups. If you want compact spheres of similarity, you have to abandon the closest friends philosophy and move to a wildly different approach.
Which is?
K-means clustering.
K-means, the absolute workhorse of machine learning. Let's call this one the team captain's method.
I love that. So the defining characteristic of K-means is that you, the human, must decide up front exactly how many clusters you want.
So I have to guess the answer before I start.
Kind of, yeah, that number is K. If you look at your whiteboard and decide you want 3 clusters, K equals 3.
Okay, so K is 3. What's step 1?
The algorithm begins by taking 3 completely random points in space and designating them as the centers, the team captains.
They just parachute out of the sky?
Literally. They drop in blindly and land on completely random coordinates on the whiteboard.
Okay, so I've got 3 random captains standing on the board. Then what?
Then step 1 begins. Every single data point on the board calculates its distance to Captain 1, Captain 2, and Captain 3.
So every dot looks around to see who's closest.
Yes, and every point then conceptually runs over and joins the team of the captain it's currently closest to. The entire board is now rigidly partitioned into 3 territories.
But wait, those territories are based on captains that just dropped in blindly. The captains aren't actually standing in the logical center of the dots that just joined their team. They might be way off on the edge of their own territory.
Exactly, which triggers step 2. The team captains look at all the dots that just pledged allegiance to them, and they recalculate their own position.
So the captain physically moves to the exact geographic center, the average of their newly formed team.
You got it. They shift to the literal middle of the pack.
Okay, but the moment the captain shifts, the boundaries change.
Yep.
Like a dot that was sitting right on the border between Team 1 and Team 2 might suddenly look up and realize, wait, Captain 1 just moved away from me and Captain 2 just moved closer. I'm switching teams.
And that is the beautiful, iterative tick-tock of the algorithm. You assign the points to the closest captain, which forces the captain to move to the new center.
And because the captain moved, you have to reevaluate all the points.
Exactly. Point switch teams. Because point switch teams, the average shifts again, so the captains move again.
Assign points, move captains. Assign points, move captains.
You just loop this over and over.
Until when? When does it stop?
Until the system exhausts itself. It stops when the captains recalculate their average and realize they don't need to move a single millimeter because no points want to switch teams anymore.
Wow. So the system just converges, the geometry locks into place?
It locks into place.
But wait, I have a major pushback here based on how we started.
Bring it on.
We literally dropped these captains out of an airplane completely blind. What if they land in terrible spots?
What do you mean?
Imagine our whiteboard has a massive, dense clump of dots in the top left and another huge clump in the bottom right. What if both of our parachuting captains randomly land right on top of each other, way down in the bottom left corner, completely missing the actual data?
You have just identified the absolute Achilles heel of K-means.
So it can fail.
It can fail spectacularly. Mathematically, the algorithm is guaranteed to converge in a finite amount of time. It's what we call a hill climbing optimization.
Meaning what?
Every single time a point switches teams or a captain moves, the total error, the total distance between points and their captains goes down. It will never make a move that makes the grouping worse.
Okay, so it's always improving.
Yes, but because it only looks at the immediate local improvements, it can easily get stuck in what is called a local optimum.
Meaning it found a configuration that looks good from its narrow, immediate perspective, but it's completely blind to a vastly superior arrangement that exists on the other side of the board.
Precisely. It climbed a small hill, entirely unaware there is a massive mountain right behind it. If the captains start in pathological locations, they will settle into a stable but practically useless configuration.
So how do we fix that? Do we guide the drop?
The industry standard solution to this problem is delightfully brute force.
Oh, I love a brute force solution. What is it?
Random restarts.
Really? You just do it again?
Yep. If you know the algorithm is highly sensitive to its starting conditions, you simply run the entire process 20 times from scratch, dropping the captains in 20 different random starting configurations.
You let them all converge 20 different times.
And at the very end, you simply look at the 20 final results and pick the one that has the absolute lowest total error.
That is so beautifully pragmatic. If the blind drop ruins the mission, just keep dropping them until you get lucky.
Exactly.
Huh.
But even with a perfect drop, k-means has another inherent issue.
What's that?
It forces an incredibly rigid, hard boundary. A point on that whiteboard is either 100% on team red or it is 100% on team blue. There is zero gray area.
Right. What if a data point is sitting perfectly on the fence, exactly equidistant between the two captains?
That rigid binary is a huge limitation, which introduces the need for soft clustering.
Soft clustering.
Yes, pioneered by an algorithm called expectation maximization, or EM.
Okay, walk me through EM. How does it soften those hard borders?
Instead of forcing points to make a hard all-or-nothing choice, EM uses the language of probability. We don't imagine our clusters as solid territories with borders anymore.
What are they then?
We imagine them as overlapping Gaussian distributions. Think of them like clouds of fog sitting on the whiteboard.
Okay, clouds of fog.
The absolute center of the cloud is incredibly dense, thick fog. As you move away from the center, the fog gets thinner and thinner, but mathematically, it theoretically extends outward forever.
So a data point isn't trapped inside a container. It simply sits in a spot on the board where different fogs are mixing.
That mixing is the key. A point sitting directly between the red center and the blue center might look at the fog density and determine it is 55% in the red cluster and 45% in the blue cluster.
So it holds partial membership in both.
Exactly. During the first phase, the expectation step, the algorithm calculates these fractional percentages for every single point on the board.
And then what? Do the centers move like in k-means?
They do. In the maximization step, we recalculate the centers of the fog clouds, but we use those percentages as gravitational weights.
Okay, let me make sure I understand this. So when the red captain calculates its new center, it doesn't get to use 100% of that border point's weight.
Right.
That 55-45 point only pulls the red center toward it with 55% of its normal strength, and it pulls the blue center with 45% of its strength. The points are tugging on the centers proportionally.
You've got it perfectly. And what that visual reveals is a system that maps much more elegantly to the real world.
Because real-world categories blur continuously.
Yes. Things are rarely separated by rigid mathematical lines. As the old song goes, sometimes a data point is a little bit country and a little bit rock and roll.
I love that. EM acknowledges the inherent ambiguity of the universe. It allows a point to express uncertainty.
It is a beautiful philosophy.
But mechanically, it sounds like an absolute nightmare.
Oh, it's computationally heavy. Why do you say that, though?
Well, you said the fog extends forever, right? Doesn't that mean every single point on the board has at least a microscopic fractional relationship with every single cluster?
It does. A point on the extreme far right of the board might be calculated as being 99.99999% in the right-hand cluster and 0.0001% in the left-hand cluster.
You are managing an infinite space of probabilities.
Exactly. Because of this, EM, unlike k-means, never truly mathematically stops.
Wait, really? The captains never completely freeze?
Never. They just move by increasingly microscopic fractions of a millimeter until the changes become so irrelevant that we just artificially pull the plug and call it a day.
Okay, so we've explored 3 distinct philosophies now. Single linkage builds sprawling chains based on closest friends. K-means creates rigid teams based on shifting averages. And EM creates fuzzy, infinite probability clouds.
That's the landscape.
So my question is there a holy grail here? Is there one ultimate algorithm that takes the absolute best elements of all 3 and creates the perfect cluster?
Asking for the perfect algorithm leads us directly to a very famous and honestly somewhat sobering mathematical proof.
Uh-oh.
It was written by the computer scientist John Kleinberg. It is universally known as the impossibility theorem of clustering.
An impossibility theorem. I love when mathematics forcefully tells us that we cannot have nice things.
It really does put us in our place.
Yeah.
Kleinberg approached the problem from the outside in. He didn't try to build an algorithm. He asked what a perfect one would it theoretically look like.
Okay, setting the standard.
He defined 3 core, highly logical properties that any rational human being would agree a good clustering algorithm must possess.
Okay, let's see if I can derive these. If I'm building the perfect algorithm, the very first thing I'd want is flexibility.
Explain what you mean by that.
Well, it shouldn't be locked into only ever making two clusters or only ever making circles. Depending on how the data is scattered, it should be able to produce any possible arrangement of groups.
That is exactly the first property. Kleinberg called it richness. The algorithm must have the capacity to output any possible partition of the data given the right distances.
Okay, richness. What else would you want?
Think about scale.
Oh. Well, obviously, it shouldn't care about my ruler. Like, if
No.
I measure the distances between all my objects in inches and run the perfect algorithm, I get my clusters.
Right.
If I open my spreadsheet, convert all those inches into miles, and run it again, the actual physical structure hasn't changed, just the scale. The algorithm should give me the exact same clusters.
Spot on. That is the second property. Scale invariance, zooming in or zooming out uniformly, should not alter the fundamental groupings.
Okay, richness and scale invariance. What's the third?
The final property is perhaps the most intuitive of all. Let's say you run your algorithm and it successfully groups your data.
Okay.
What happens if you take the points that are inside a shared cluster and magically push them even closer together while simultaneously taking the points in different clusters and pushing them even further apart?
So if I take a group of friends and make their bond even tighter, and I take strangers and make them actively move away from each other,
Yes.
what should happen to the clusters?
The social circle shouldn't break. The existing structure is just being exaggerated and reinforced. The algorithm should output the exact same clusters as before.
Kleinberg called that consistency. If similar things become more similar and dissimilar things become more dissimilar, the underlying partition must survive.
Okay, so richness, scale invariance, and consistency. Three highly rational foundational requirements for a good clustering algorithm.
And the twist. Let me guess. They are mathematically incompatible.
Kleinberg mathematically proved that it is absolutely impossible for any clustering algorithm to possess all three properties simultaneously.
Wow. So the concept of perfect clustering is literally a ghost. It doesn't exist.
It is a mathematical illusion. You cannot have it all. If you engineer an algorithm that is perfectly scale invariant and perfectly consistent, you will mathematically destroy its richness. It will lose the ability to form certain shapes.
It's an eternal game of trade-offs.
Completely. You have to look at your specific data set, look at your specific goal, and decide which of those three mathematical pillars you are willing to compromise. Clustering is not about discovering the objective truth of the universe.
What is it about them?
It's about finding a useful lens through which to view your data based on your immediate needs.
That is wild. It's exactly like cartography.
Oh, how so?
Finding a perfect flat map of the Earth is mathematically impossible because you cannot flatten a 3D sphere onto a 2D piece of paper without tearing or stretching it. You have to pick your poison.
That's true.
Like, you use the Mercator projection, which preserves the shape of the coastlines for sailors, but it wildly distorts the size of Greenland, making it look larger than Africa.
No.
Or you use a Peters projection, which gets the sizes right, but stretches the shapes until they look melted. You accept the distortion that hurts your specific mission the least.
That cartography analogy maps perfectly to the clustering dilemma. You are projecting complex reality onto a simplified model, and distortion is absolutely mandatory.
Man, that's fascinating. Okay, so we've accepted our mathematical compromises, and we have grouped our data. But that assumes our data is, manageable.
Manageable is a luxury in data science.
Right. What if we are facing a vastly different problem? What if we just have too much data? Not just too many objects, but what if every single object we are analyzing has thousands and thousands of different attributes?
You're talking about columns in a spreadsheet.
Exactly. We have to figure out how to shrink the haystack so the algorithm can actually find the needle.
Now you are crossing the border from clustering into feature selection. And the reason this transition is so critical, the reason it keeps data scientists awake at night, is a phenomenon known as the curse of dimensionality.
The curse of dimensionality. It sounds like a psychological thriller set in deep space.
It is the ultimate villain of machine learning, honestly. The dimensions are your features, your columns in the spreadsheet. The curse dictates that every time you add a new feature, the volume of the mathematical space your data lives in grows exponentially.
It just balloons outward.
The space expands so rapidly and becomes so incredibly vast that your data points end up isolated and completely lonely in this massive high-dimensional void.
And if they are isolated in the void, the algorithms we just talked about, like k-means, break down because the distance between everything becomes massive and meaningless.
Exactly. The concept of a neighborhood vanishes.
Let me try an analogy here to ground this. Imagine I'm trying to build a spam filter for my email inbox.
Okay, classic problem.
If I want the algorithm to detect spam, I don't need to feed it the font size of the email, the background hex color, the precise millisecond it was sent, the browser the sender used, and the IP
That's
address.
way too much noise.
Right. If I feed all 50 of those dimensions into an algorithm, it's going to get totally overwhelmed trying to find a pattern in the font colors. The space is too big. I really just need to extract the two features that actually matter. Does the email contain the words Nigerian prince? And does it contain the words wire transfer?
That is the absolute essence of feature selection. You must identify the signal and ruthlessly discard the noise. But the sheer combinatorics of it make it a brutal task.
Because there are so many combinations to test.
Right. If you have n possible features, the number of distinct subsets you could theoretically create to test is 2 to the power of n.
Oh, wow.
It is an exponential explosion. Testing every single combination of features is mathematically classified as an intractable problem. You simply do not have enough computing power in the universe to check them all.
So if we literally can't test every combination, what are the workarounds? How do we build the team?
The field generally divides the solution into 2 distinct camps: filtering and wrapping.
Let's start with filtering.
Filtering is incredibly fast, and it's computationally cheap. The philosophy is to evaluate every single feature in total isolation, completely independent of the actual learning algorithm you plan to use later.
Like grading them on a curve.
Exactly. You look at a feature, like font size, and you ask a statistical question. Does this feature have a high variance? Or does knowing this feature give me high information gain about whether the email is spam?
So you just score every feature individually.
They score them, rank them from best to worst, keep the top 10, and throw the rest in the garbage.
Okay, so filtering is exactly like the NFL scouting combine.
Oh, I like this. Go on.
You have 300 athletes. Those are our features. You do not have the time or the money to let all 300 of them play a full season of actual football games to see who works well together.
Because that would be intractable.
Right, so you just line them up in a gym and measure them in a vacuum, run a 40-yard dash, lift this heavy weight. You evaluate their isolated metrics, draft the fastest runners, and just pray they form a cohesive football team.
Taking that combine analogy further, it perfectly highlights the inherent flaw of filtering.
Which is?
Being fast in a 40-yard dash does not guarantee you are good at reading a defense during a game. Filtering completely ignores how features interact with each other.
Oh, that makes sense.
And critically, it completely ignores the specific biases, strengths, and weaknesses of the actual machine learning algorithm you are going to use down the line.
Right. A player might look completely useless in a solo drill. They are slow, they aren't strong. If you just filter, you cut them. But maybe that specific player has an incredible telepathic synergy with your quarterback that you will never discover unless you actually put them on the field together.
Which brings us directly to the second camp, wrapping. Wrapping is incredibly slow, but it is deeply accurate. In wrapping, you do not test features in a vacuum. You test subsets of features by actually running your specific learning algorithm and checking the final error rate.
You let them play the scrimmage.
You let them play the scrimmage.
But wait, you just told me checking every possible combination of a scrimmage is exponentially impossible. We can't let every conceivable subset of players play a full season.
We cannot check them all, so we use guided search strategies. The most common is forward sequential selection.
How does that work?
You start with a completely empty roster. You let every single player try out one-on-one. You find the absolute best solo player, and you put them on the team permanently.
Okay, so we have our star player.
Then you test every remaining player, but this time they play in combination with your star. You are looking for the player who adds the most value to the existing roster.
Oh, so whoever forms the best duo, you keep.
Yes. Then you test for the best trio. You slowly build the dream team, one optimal addition at a time.
That's brilliant. And I imagine the inverse is true as well.
Backward elimination. You put every single player on the field at the exact same time. It is massive, high-dimensional chaos.
Right.
Then you systematically remove one player at a time and run the scrimmage. Whoever's absence causes the least amount of harm to the team's overall score, they get cut.
You just keep whittling the team down player by player until removing anyone else would actively ruin the team's performance.
Exactly. So that's filtering and wrapping.
That makes total intuitive sense.
Yeah.
Filtering is the combine, wrapping is the scrimmage. But I want to push back on a conceptual edge case here.
Let's hear it.
Let's say I am looking at a data set about housing prices, And by some clerical error, two of my columns are literally identical. I have a column for square footage and another column right next to it that is the exact same square footage.
Okay, perfectly duplicated data.
Is one of them completely useless? Should I just throw it away?
You are brushing up against a very profound theoretical distinction in machine learning right now. It's the stark difference between relevance and usefulness.
Relevance and usefulness. Aren't those the same thing?
Not at all. To truly unpack this, we have to invoke a theoretical construct known as the Bayes optimal classifier.
The Bayes optimal classifier. It sounds like the final boss of statistics.
It is essentially the God mode of algorithms. It represents the absolute mathematical ceiling of classification performance.
What makes it God mode?
It assumes you have infinite computing power and that you know the true underlying probability distributions of the entire universe. It never makes a mistake that could theoretically be avoided.
Okay, so we have an omniscient algorithm. How does that help with my duplicate columns?
We use the Bayes optimal classifier to define the concept of relevance. A feature is considered strongly relevant if removing it actively degrades the performance of the Bayes optimal classifier.
So if God mode messes up without it.
Meaning, that specific feature contains unique underlying information about the structure of reality that cannot be found anywhere else in your data set.
Let me test that. If I go back to my spam filter and I delete the feature Nigerian prince, and my omniscient God mode algorithm suddenly gets worse at catching spam, that proves Nigerian prince is strongly relevant. The universe demanded that information.
Yes. Now, apply that test to your twin square footage columns. Are they strongly relevant?
Let's see. If I delete the first column, does the God mode algorithm get worse? No, because it simply shifts its gaze to the second identical column. No structural information about the universe was lost.
Therefore, the first column is not strongly relevant.
But wait, the second column is exactly the same. If I delete the second column instead, the algorithm just uses the first one and is perfectly fine. So neither of them are strongly relevant.
This is a classic paradox. It's known as the evil twin or kryptonite problem. Introducing a perfect copy of a feature mathematically destroys its strong relevance.
Yeah.
You go from being absolutely indispensable to being completely mutually replaceable. Instead, we classify those features as weakly relevant. They contain excellent, valid information, but you do not strictly need both of them to achieve optimal performance.
Okay, so relevance is deeply tied to the pure, raw information content of the universe. It doesn't care of the algorithm at all. What about usefulness, then?
Usefulness is the exact opposite. Usefulness is entirely dependent on the specific, flawed, mechanical reality of the real-world algorithm you are actually trying to run.
Give me an example of that.
I can give you a mind-bending scenario to prove this. Imagine a feature column in your spreadsheet that is pure noise, a column where every single data point is simply the number one.
A column of solid ones has zero variance. It tells me absolutely nothing about how data point A differs from data point B.
Right.
The God mode algorithm would completely ignore it. It is entirely irrelevant.
It is 100% irrelevant to the universe.
Where?
What is the specific flawed algorithm you are using is a very basic, primitive neural network node, a perceptron.
Okay, a perceptron.
A standard perceptron is essentially a mathematical machine that tries to draw a straight line through a graph to separate data. But by default, its internal math forces that line to perfectly pass through the origin point, 0, 0.
Okay, so the line is anchored at the bottom corner.
If your actual data requires a line that is shifted high up on the y-axis to separate it properly, your perceptron will fail miserably. Its line is stuck at the origin, unless you give it that column of pure ones.
Wait, how does a column of ones help?
Because geometrically, the perceptron can take that column of constant ones, apply a weight to it, and use it as a bias unit.
A bias unit.
It acts as a mechanical lever that allows the perceptron to physically lift this line off the origin and shift it anywhere on the graph, solving the problem perfectly.
That is absolutely insane. So a feature that contains literally zero information about the universe, a completely mathematically irrelevant feature, can magically become incredibly useful simply because it acts as a mechanical crutch for a dumb algorithm's geometry.
Exactly. Relevance is about truth. Usefulness is about mechanics. A feature can be deeply relevant, but completely useless to a specific algorithm that can't process it. And a feature can be completely irrelevant, containing zero truth, but be wildly useful.
Okay, my mind is slightly blown by the bias unit trick.
That's a fun one.
We have grouped our data with clustering. We have thrown away the useless and irrelevant data with feature selection. But here is where we hit the most fascinating barrier.
Okay.
What if the true signal we are searching for isn't a column we can just select? What if the signal is hidden between the features? What if we can't just pick players for the team, but we need to literally melt them down in a forge and create completely new players out of their raw materials?
Now we have crossed from feature selection into feature transformation. We are no longer picking and choosing. We are morphing reality.
Morphing reality. I love the sound of that.
And there is no better way to understand why this is mandatory than the Google problem, known academically as ad hoc retrieval.
Okay, let's set the stage for this. I open my laptop, I go to a search engine, and I type in the words machine learning.
And the search engine instantly has to scan billions of text documents to find what you want. If the features the search engine uses are just literal words, then feature selection alone will completely fail to solve this problem.
Why?
It fails because of two fundamental structural flaws in human language: polysemy and synonymy.
Polysemy. That's when a single word has multiple completely different meanings, right?
Let's look at the word car. To 99% of the world, car means an automobile.
Sure.
But if you are an old-school software engineer programming in Lisp, car is a fundamental foundational coding function that extracts the first element of a list.
Oh, wow.
So if you just search for the literal feature car, the search engine will return a flood of false positives. It will hand you dense Lisp programming manuals when you actually wanted to buy a Tesla. The literal word is entirely ambiguous.
And synonymy is the exact inverse of that. Multiple different words that mean the exact same thing.
Exactly. If you search for car, and the search engine only looks for that specific string of letters, you might miss a brilliant, definitive article about the automotive industry simply because the author chose to only use the word automobile.
You get a false negative, the information you wanted is sitting right there, but the literal feature didn't match.
And feature selection cannot fix this, because the problem isn't that you have too many words. The problem is that words are deeply flawed vehicles for underlying concepts. To solve the Google problem, we must melt the literal words down and transform them into mathematical concepts.
Okay, but how do we achieve that alchemy? How do we melt words into concepts?
One of the oldest, most powerful, and highly visual tools for this is principal component analysis, or PCA.
Principal component analysis. Let's try to paint a clear visual of PCA for the listener driving right now.
Let's do it.
Imagine a 3D scatter plot hovering in the air in front of you. You have plotted thousands of data points, and together they form a distinct shape. Let's say they form a long, stretched-out oval, kind of like an American football that is tilted upward and to the right.
That visual is perfect.
Yeah.
PCA looks at that hovering football of data, and it ignores the standard X, Y, and Z axes. It asks a completely new geometric question.
Which is?
If I have to draw a single straight steel rod right through the center of this data that captures the absolute maximum amount of spread, the maximum variance, what angle do I push that rod through?
Well, if you want to capture the most spread, you would push the rod directly down the long axis of the football, from tip to tip. That is the longest possible path through the data.
That rod becomes your first principal component. It is a brand new feature forged out of a linear combination of your old axes. It represents the primary direction of the data.
Okay, so we have one rod.
Then PCA takes a second rod, and it forces it to be entirely perpendicular orthogonal to the first rod. It pushes this second rod through the football to capture the remaining variance, which would be the thickness of the football.
Oh, I see. PCA essentially builds a whole new custom coordinate system tailored specifically to the unique shape of your data.
Exactly. And because our ultimate goal is usually reducing the size of our data, we look at this new coordinate system and we just throw away the short axis.
We keep the long rod that goes from tip to tip, preserving the main structure, and we throw away the short rod that measures the skinny width.
We have compressed the data into fewer dimensions, but we haven't lost the core shape.
That makes total sense. PCA is fantastic for data reconstruction. If you drop the minor components, you can still rebuild a very close approximation of the original data with minimal squared error.
But, and there's a big but, because it relies on maximum variance and forcing every new axis to be perpendicular, it does something visually bizarre when applied to complex images.
Like what?
When you feed PCA thousands of photographs of human faces, what do you think that first rod, that first principal component of maximum variance actually looks like?
Well, if it's finding the most important feature of a face, I would guess it finds the eyes. Or maybe the structure of the nose?
It doesn't find a facial feature at all.
It doesn't.
The first component is essentially just brightness. It is the overall illumination of the face. Because lighting varies so wildly from photo to photo, that is where the maximum mathematical variance lives.
Wow, just the lighting. What about the second component?
It looks like a terrifying, blurry, generic ghost face.
A ghost face.
Because PCA is a global algorithm that forces its axes to be mathematically orthogonal, it simply smashes all the faces together into global average components.
It finds the overarching average, but it completely fails to isolate the individual parts of a face.
Exactly. If you want to dissect the data into its independent localized parts, you have to abandon the orthogonal constraints of PCA. You need an algorithm with a fundamentally different philosophical view of the universe.
And what algorithm is that?
You need independent component analysis, ICA.
ICA. And to truly grasp the magic of ICA, we have to talk about the cocktail party problem. This is my absolute favorite thought experiment in all of machine learning.
It's a classic for a reason.
Let's paint the scene. Picture a loud, chaotic, crowded cocktail party. In the center of the room, you have three people standing in a tight circle, deep in an animated conversation. Person A, person B, and person C. They are all talking over each other simultaneously.
And hidden around the room, let's say we have placed 3 microphones. Microphone 1 is near the punch bowl, microphone 2 is on the ceiling, and microphone 3 is by the door.
Okay.
Because they are in different physical locations, the microphones record slightly different mixes of the room. Microphone 1 might hear person A slightly louder, while microphone 3 hears person C slightly louder.
But fundamentally, every single microphone is recording a chaotic, jumbled, linear combination of all 3 voices mixed together.
Yes. If you put on headphones and listen to just microphone 1, it sounds like unintelligible gibberish. You cannot mentally untangle the overlapping audio waves.
But ICA can untangle them.
It can, and it does so by making a massive, profound assumption about the physical universe.
What's the assumption?
It assumes that the underlying hidden causes, the 3 human beings talking, are statistically independent of each other, meaning the specific sound wave coming out of person A's vocal cords contains absolutely zero mutual information about the sound wave coming out of person B's vocal cords. They were independent physical processes.
So ICA takes the 3 messy, jumbled microphone tracks and it mathematically twists, rotates, and unmixes them. It keeps adjusting the math until it finds 3 new tracks that have absolutely zero statistical correlation with each other.
It actively maximizes statistical independence. And miraculously, when the math finally settles, when the correlation drops to 0, the 3 tracks it spits out are the isolated, crystal clear individual audio recordings of person A, person B, and person C.
That is wild.
By simply demanding independence, it mathematically unbakes the acoustic cake.
Unbaking a cake is basically magic. But here is where ICA moves from clever math to genuine philosophy. You mentioned earlier that when you feed human faces to PCA, it spits out blurry, average ghost faces.
Right.
What happens when you feed a massive database of human faces into the unbaking magic of ICA?
This is where the algorithm touches reality. When you feed faces to ICA, it doesn't find averages. It isolates a component that represents a left eye. It finds a distinct component for a nose, a component for a mouth.
Because it's looking for independent parts.
Because ICA is looking for statistically independent causes, it naturally isolates the distinct local features that independently vary from face to face.
And what if we step entirely outside of human faces? What if we feed it 1 million photographs of raw nature, trees, rocks, grass, clouds? If ICA breaks things down into their independent atomic parts, what are the independent components of the natural visual world?
It finds edges.
Edges, just sharp lines of contrast.
Edges. According to the deep mathematics of ICA, the fundamental independent building blocks of all visual reality are simply sharp transitions from light to dark.
Wow.
And if you shift domains and feed ICA millions of text documents, the independent components it unbakes are topics, groups of words that naturally co-occur together, independently of other groups. ICA operates like a digital microscope, revealing the foundational atoms of whatever universe you point it at.
Finding edge detectors in nature photos, it's almost eerily biological. That completely mimics how the human visual cortex evolved. Our brains literally have specific neurons that are hardwired to only fire when they see edges and contrasting lines.
It is a profound convergence. A purely mathematical algorithm, seeking only statistical independence, organically recreates the biological architecture of the mammalian brain.
That is awe-inspiring. But on a practical level, both PCA and ICA sound incredibly mathematically heavy. They require calculating covariance matrices, maximizing independence, untangling complex signals. It takes massive amounts of computing power.
It does. It's not cheap.
What if I am a data scientist on a deadline, and I simply don't have the time or the processors for that? What if I just want to throw my high-dimensional data at the wall and see what sticks?
Then you, my friend, are looking for the absolute chaotic joy of RCA, random component analysis, often referred to as random projections.
Just based on the name, let me guess. Instead of carefully calculating the angle of maximum variance or meticulously solving for statistical independence, I just ask a computer to generate a massive matrix of completely random numbers, and I violently smash my data through it.
You literally pick entirely random directions in multi-dimensional space and you project your data onto them.
That sounds like it absolutely should not work. It sounds like throwing a bucket of mixed paint at a canvas and expecting it to instantly form the Mona Lisa.
It will absolutely not give you the Mona Lisa.
Hmm.
If your goal is to cleanly reconstruct the original image, RCA is a complete disaster. But here is the bizarre, counterintuitive secret of high-dimensional geometry. If you have a data set with thousands and thousands of dimensions, and you randomly project it down into a much smaller space, say a few hundred dimensions, the relative distances between the data points are largely preserved.
Wait, explain how that is geometrically possible. How does the structure survive the random smush?
Think of it like a flashlight and a shadow. Imagine a complex 3D wireframe object hovering in a room.
Okay, a wireframe.
If you shine a flashlight on it from a completely random angle, it casts a flat 2D shadow on the wall. That shadow is a random projection. You've lost a massive amount of detail. You can't reconstruct the full 3D object from that one single shadow.
Sure.
But if two intersecting wires were physically touching each other in the 3D object, their shadows will still be touching on the wall. If two wires were far apart, their shadows will likely remain far apart. The localized relative distances, the core correlations, survive the dimension reduction.
Ooh, so the signal survives the random smush. And if my ultimate goal isn't to draw a perfect picture, but simply to fill that data into a classifier down the line like a spam filter, RCA works astoundingly well because the points that were close together in the massive space are still close together in the small space.
Exactly. And the greatest advantage of RCA, it is unbelievably fast. Generating random numbers and doing basic matrix multiplication is the cheapest, fastest thing a modern computer can do.
So you bypass the heavy math entirely.
You don't have to earn your complexity. You just roll the geometric dice and it works.
Fast, cheap, and geometrically out of control. I love it. And just to briefly round out our transformation toolkit, we should probably mention LDA, linear discriminant analysis.
Right. LDA is a bit of an outlier in this specific conversation because it is actually a supervised method.
Oh, it uses labels.
Yes. Unlike PCA or ICA, LDA actively looks the labels. It tries to find the specific geometric projection that most violently separates the different classes of data. It actively seeks the best discriminating lines, making it highly focused on downstream classification rather than purely describing the raw, unlabeled structure.
Okay, let's take a breath and survey the landscape. We have journeyed deep into the wilderness today. We took raw, unlabeled chaos and grouped it using k-means and expectation maximization.
We did.
We shrunk the massive haystack by filtering and wrapping features. We forged entirely new concepts using the global averages of PCA, the edge-detecting magic of ICA, and the shadow-casting speed of RCA.
It's a massive toolkit.
But underneath all of these algorithms, we keep brushing up against a very specific, incredibly heavy word. We keep talking about measuring information gain, mutual information.
Which brings us to our final and perhaps most foundational destination. What is information? How do we mathematically weigh the value of a signal?
To understand this, we have to travel back in time, mid-20th century, the 1940s, Bell Labs.
Ah, the golden era.
It's the dawn of modern telecommunications. Engineers are dealing with massive networks of copper wire, telegraph lines, and early long-distance telephones. And they have a very practical, highly capitalistic problem to solve. How do you charge a customer for sending a message?
Do you charge them by the word? Do you charge by the literal electrical pulse.
Exactly. It was a crisis of measurement. And into this intensely practical problem steps a mathematician named Claude Shannon, the undisputed father of information theory.
Shannon is a legend.
Shannon realized that human language was a terrible metric for data. A 10-word message could contain a massive, life-altering revelation, while a 100-word message could be completely hollow filler containing almost no meaning.
So counting words is useless.
Right. He needed a strictly mathematical way to measure the actual amount of surprise contained in a signal. And to find it, he didn't look to linguistics. He looked to thermodynamics. He borrowed the concept of entropy.
Entropy. I remember learning about Maxwell's demon in physics class. This idea from the 1800s where a tiny imaginary demon controls a door between two chambers of gas.
Yeah, that's the one.
If the demon knows the exact speed and trajectory of every gas molecule, it can open the door to let the fast, hot molecules on one side and the slow, cold molecules on the other, theoretically reversing the entropy of the universe just by possessing knowledge.
It proved that information and physical reality, the disorder of the universe, are deeply intertwined.
That thermodynamic link is the key. Information is fundamentally tied to the predictability of the universe. To understand Shannon's genius, we have to strip away all the complexity of computers and copper wires and do a very pure thought experiment.
Let's do it. Imagine I am an operator in Atlanta and I need to send a telegram to you, sitting in an office in San Francisco. My message is going to consist of exactly 10 coin flips, heads or tails.
Okay, 10 coin flips. Let's run scenario 1. Before you go to the telegraph machine, I secretly hand you a severely biased trick coin. It has heads stamped on both sides.
Okay, a two-headed coin.
You sit at your desk in Atlanta, you flip it 10 times, and you write down the results. Then you put your hand on the telegraph key to transmit this sequence to me in San Francisco. But wait, I am the one who gave you the coin. I already know you are using a two-headed coin.
So before I even tap the first electrical pulse, you already know the message is going to be 10 heads.
Precisely. From my perspective in San Francisco, there is absolutely zero uncertainty about what you're going to send. There is zero surprise. Therefore, according to the mathematical laws of Claude Shannon, transmitting that message requires exactly 0 bits of information.
Because you already know it.
You don't even need to send it. The signal is completely empty.
But scenario 2 changes the physics entirely. I throw away the trick coin and I pull a perfectly fair 50-50 quarter out of my pocket. I flip it 10 times. I get a completely random sequence, heads, tails, tails, heads, tails.
Now, the physics of the communication change entirely. I am sitting in San Francisco, and I have absolutely no idea what sequence you are looking at. Every single time you tap that telegraph key, the result is a total surprise to me.
Because it's a fair coin.
Right. To figure out the result of your very first flip, I would have to ask you a binary yes-no question. Was it heads?
And one yes-no question equals one exact bit of information.
Exactly. 10 random flips require me to ask 10 yes-no questions to resolve the uncertainty. The entropy, the randomness of the system is maximized. High surprise inherently equals high information.
This is such a massive paradigm shift. It means that information has absolutely nothing to do with meaning or poetry or human emotion. A Shakespeare sonnet and a string of random numbers are judged by the exact same metric.
Information is strictly a mathematical measure of unpredictability.
Yes. Entropy calculates the absolute minimum number of yes-no questions you must ask to accurately transmit a symbol. And this mathematical revelation completely revolutionized how we engineer communication. It leads directly to the concept of variable length encoding.
Which is essentially the logic behind Morse code, right?
It is the exact underlying logic of Morse code. If you analyze the English language, the letter E and the letter T appear constantly. They are highly predictable.
Therefore, they carry very little surprise and very low entropy.
Exactly. So when designing Morse code, you assign them the shortest possible symbols. E is a single, quick dot. T is a single dash. But what about the letter Z?
Z is incredibly rare. If a Z shows up in a message, it is a massive surprise.
High surprise, high entropy. So Z is assigned a long, complex, resource-heavy code. Dash, dash, dot, dot. You optimize the entire communication network by ruthlessly assigning short codes to low entropy, predictable symbols, and hoarding the long codes for the high entropy, surprising symbols.
That is brilliant optimization. But what happens when things aren't isolated? How do we measure the space when variables interact with each other?
What do you mean?
For example, if I look out my window right now and see dense black clouds raining heavily, that visual data drastically reduces my uncertainty about whether I'm going to hear a crack of thunder in the next 5 minutes. The rain and the thunder are linked.
Now you are stepping into the realm of mutual information. Shannon gave us tools to measure interactions. We have joint entropy, which measures the total combined randomness of two variables existing together.
Okay.
We have conditional entropy, which asks how much randomness remains in variable y after you are already fully aware of variable x. But mutual information is the true magic number.
What does that measure?
It is the precise mathematical measure of how much the knowledge of one variable actively reduces the randomness, the surprise, of another.
So if I have two coins and they are miraculously magnetically linked through quantum entanglement so that if coin A lands on heads, coin B is 100% guaranteed to also land on heads.
Yeah.
What is the mutual information?
The mutual information in that entangled state is one. It is complete, perfect knowledge transfer. Knowing the state of coin A tells you absolutely everything there is to know about coin B. There is no surprise left.
But if the coins are totally normal independent quarters, the mutual information is exactly zero.
Yep. Staring at the result of coin A tells you absolutely nothing about the fate of coin B.
And just to tie a neat bow on the underlying math of models, I know in advanced machine learning they often use a metric called KL divergence. How does that fit into this universe of entropy?
Think of KL divergence as the ruler we use to measure the distance between two different models of reality. If you have a true probability distribution, the actual reality of the data, and you build an artificial machine learning model that tries to approximate it, KL divergence mathematically calculates exactly how much extra information, how many extra bits you lose by using your flawed model instead of the real thing.
It measures the distance between your approximation and truth?
Exactly. Mutual information is actually just a specific geometric case of KL divergence. It is all part of the same thermodynamic toolkit used to measure the invisible space between concepts.
Okay, we have covered a staggering massive amount of ground today. Let's recap the journey.
Yes, let's.
We started out in the muddy, unlabeled wilderness of raw data. We brought order to that chaos using clustering algorithms, contrasting the rigid teams of k-means with the infinite fuzzy fogs of expectation maximization.
We learned from Kleinberg's impossibility theorem that the perfect cluster is a mathematical ghost, requiring us to choose our distortions carefully.
We then trimmed the fat from our data using feature selection, navigating the vast void of the curse of dimensionality and making the crucial distinction between universal relevance and algorithmic usefulness.
We forged completely new geometric realities, uncovering the hidden edges of the world using feature transformations like PCA and ICA.
And finally, we drilled all the way down to the bedrock with Claude Shannon, proving that the true essence of information is mathematically bound to surprise and uncertainty.
It is a profound trajectory, moving from raw, chaotic grouping all the way down to the thermodynamic definition of knowledge itself.
It really is. But before we sign off, I want to leave you, the listener, with a final lingering thought to chew on. Something that builds on everything we've unpacked today about how machines view the world.
Oh, what is the thought?
We just established, thanks to Claude Shannon and the coins, that information fundamentally requires surprise. It requires unpredictability. If I know exactly what the coin is going to do before it slips, there is zero information generated.
That is the mathematical law.
Well, think about the modern internet. Think about the recommendation algorithms running constantly on your phone, right in your pocket. They are using every single concept we talked about today.
Right, clustering, feature selection.
They use massive clustering, rigorous feature selection, and dimensional transformation to build an impossibly detailed high-dimensional profile of exactly who you are. And their entire billions of dollars goal is to actively reduce uncertainty.
Oh, I see where you're going.
They want to predict exactly what movie you will click on next, exactly what pair of shoes you will purchase, exactly what political article will trigger you to leave an angry comment.
They are massive engines designed specifically to minimize your personal entropy.
Exactly. So here's the question. If we are rapidly moving into an era where artificial algorithms are explicitly designed to make human behavior completely 100% predictable, what happens to us?
Wow.
If a machine knows your next move, your next purchase, your next thought before you even formulate it, are you generating any actual information at all anymore? Or have we, through the relentless perfection of these algorithms, slowly become the two-headed coin? Entirely predictable, always landing on heads.
That is a remarkably chilling application of Shannon's mathematics.
Something to ponder on the rest of your drive.
Thank you so much for joining us on this deep dive. Keep questioning the data around you. Keep looking for the hidden structures in the noise, and whatever you do, try to stay a little bit unpredictable.
Until next time.